God does not play dice was Einstein's poetic way of doubting Heisenberg's indeterminacy principle. But what did he expect? The hunger to misunderstand should have been palpable to him.
God does not play dice. That's something Albert Einstein once said because he was deeply uncomfortable with the quantum world, or what Marvel movies like to call the quantum realm.
Do not screw with the regulator. If that regulator is compromised, you would go subatomic.
What does that mean?
It means that you would enter a quantum realm.
But here's the question. Why did Einstein feel that uncomfortable to the point where he had to bring God into it? Well, that's exactly what we're going to explore in this video. We're about to step into a world so strange that even some of the most brilliant physicists in history had to come together just to try to make sense of it. So get your brain ready, because some of the ideas we'll talk about might genuinely blow your mind. Let's talk about it. Alright guys, this video is a continuation of our discussion about the quantum world. Now, for those of you who haven't watched episode 1 yet, I'd recommend checking that out first so you can follow the story better. But the point is, in the previous video, we saw that the quantum world exists deep inside the atom, a subatomic world whose scale is already far beyond anything humans can directly observe. And most of you probably recognize this image right here. This is how we're usually taught to imagine an atom, right? This model is known as the Bohr model of the atom. But here's the thing, guys. That picture of the atom is actually just a simplification. A simplified model made mostly for teaching students to make it easier to understand. Because when you really start diving into the quantum world, atoms are not nearly that simple. Instead, it looks more like this. Yeah, the shapes start to become strange, abstract, and there are many different forms. Something that almost doesn't even look like matter at all. But as weird as it may seem, this is actually the structure that makes up all matter in our universe. And right inside this strange-looking atom, that's where the quantum world exists. A world so bizarre that it once made Einstein say, "God does not play dice." Alright, so now let's talk about why Einstein ended up bringing God into the conversation when facing the quantum world.
He was quoted as saying, "God does not play dice with the universe." He meant that despite appearances, there cannot be fundamental uncertainty built into the laws of physics.
The line, "God does not play dice," actually points to one specific problem in the quantum world, something called wave-particle duality. Now let me ask you something. Do you guys know Naruto? In the series, there's one technique that's probably the most iconic one. That technique is... Yeah, that one. The shadow clone technique. And weirdly enough, it's actually a pretty good way to imagine how things behave at the quantum level. Sounds kind of made up, right? And that's exactly why Einstein hated the idea of the quantum world. To make this easier to picture, imagine there's a plate with two narrow slits in it. Now, if you throw sand at it, you just get a pattern like this. Simple.
And this is it. It's not really a surprise. There are two stripes, very much like the two slits. Because of course, sand consists of grains, like little particles, and they either go through one slit or they go through the other slit. And that's what you're seeing. These particles have gone through one slit, these have gone through the other slit. So this is what sand does, and this is what particles do. They produce this pattern.
But if what goes through those slits is a wave, everything changes. It can pass through both slits at the same time. And when those waves overlap, they create this striped pattern. This pattern is called an interference pattern.
The peaks and valleys would create a series of stripes and what's known as an interference pattern.
Alright, now let's move to the actual experiment. In the double-slit experiment, scientists fire particles, like electrons, toward a plate that has two slits in it. Behind that plate, there's a screen set up to observe the pattern that forms. Now let's think about this for a moment. If what we're firing are particles and particles are matter, then the result on the screen should be two lines, right? Just like the grains of sand we threw earlier. But when scientists actually performed this experiment, the result wasn't two lines. Instead, what appeared on the screen was an interference pattern, a pattern that should only be produced by waves.
But have a look at this. If we collect up all these blips collected over a time period and have a look at what the pattern is, we see something quite remarkable. The pattern you see is the pattern that waves make.
And this is where things start to get weird. How can a particle behave like a wave? Because logically, if particles are the building blocks of atoms, and atoms themselves are the building blocks of matter, then particles should be matter, right? If it's not, then how could the world of solid matter we experience every day be made of something as shapeless as a wave? And this is exactly the point where many scientists started to feel frustrated. Because in order to produce an interference pattern on the screen, the particle would first have to behave like a wave, which can pass through both slits at the same time. So scientists concluded that a single particle splits itself right before entering the slits, then travels through both slits at the same time, and somehow rejoins itself again before reaching the screen, then finally landing on the screen in seemingly random positions, which eventually formed the interference pattern. This phenomenon later became known as superposition.
The electron can somehow explore both paths, just like a wave can, and then interfere with itself to control where it lands on the screen. So that's a very strange picture of reality.
It's basically like Naruto's shadow clone technique. And of course, something like this makes absolutely no sense in classical physics. Scientists couldn't just accept that their logic was being completely messed with by tiny particles. So, they decided to try something simple. They placed a detector near the slits. They wanted to see which slit the particle was actually going through. But it turns out, placing a detector near the slits actually led them to something even crazier. Because when the detector was turned on, and the particles were fired toward the two slits again, something strange happened. The interference pattern just disappeared.
But of course, I've been cheeky here. I haven't shown you the results of the experiment.
What appeared on the screen now were just two lines, exactly like the pattern we saw when we threw grains of sand earlier. Which means the particles were now behaving like matter, not like waves anymore. They were only passing through one of the two slits. But when the detector was removed, when nothing was watching the particles anymore, the interference pattern just reappeared. The particles started behaving like waves again. Yeah, it's almost as if these particles somehow know whether they're being observed or not. If we observe them, they behave like matter. And if we don't, they behave like waves. And do you see the problem here? The problem is, does the world still exist when we close our eyes? Does it still have the same form when no one is looking at it? Even Einstein himself once asked a question during this confusion. Does the moon still exist when no one is looking at it? And because of all this confusion surrounding quantum physics, the most influential scientists in the world eventually gathered in one place to discuss it. They met at the 5th Solvay Conference, which was held in Brussels, Belgium in 1927. Now, if you're into physics, you've probably seen this legendary photo, a moment where figures like Albert Einstein, Niels Bohr, Schrödinger, Max Planck, Marie Curie, Paul Dirac, and many other brilliant physicists gathered together in one place. You could almost think of it like the Avengers meeting in real life. And just like the conflict between Tony Stark and Captain America, the Solvay Conference also witnessed one of the most famous rivalries in the history of science, a debate between two giants of physics, Albert Einstein and Niels Bohr. This conflict began with a conclusion proposed by Bohr. At the time, Bohr argued that quantum theory was essentially complete, supported by the uncertainty principle and the Schrödinger equation. But Einstein openly rejected that conclusion. According to Einstein, the quantum world simply had not yet been fully understood. That didn't mean the universe itself was random or fundamentally uncertain. And that's exactly why Einstein once said, "God does not play dice." According to Einstein, it was impossible that God created the universe by rolling dice, leaving reality to pure uncertainty. But Bohr saw things very differently. For him, the quantum world really does operate in an uncertain way. So Bohr pushed back and replied, "Einstein, stop telling God what to do." And because of that, the world of physics became divided into two camps. Most scientists supported Bohr's view, while a smaller group stood with Einstein. And honestly, doesn't this feel like the Avengers Civil War, but in real life? Frustrated with Bohr's position, Albert Einstein, with two of his colleagues, Boris Podolsky and Nathan Rosen, proposed a paradox that later became known as the EPR paradox. At first, Einstein intended this paradox as a challenge to Bohr's conclusions. Through this idea, Einstein wanted to show that there might still be something missing from quantum theory. But instead of weakening quantum theory, EPR paradox actually pulled us even deeper into the weirdness of the quantum world. In fact, Einstein himself described it as spooky action at a distance. And if we translate that idea loosely, it almost sounds like something straight out of voodoo. Yeah, the African black magic. But sorry guys, we can't dive into that phenomenon in this video. The topic itself is pretty heavy, and it deserves its own discussion. For now, the most important thing to take away from this video is that the quantum world is just crazy as hell.